Hello, we are Jun Park, Donghan, Yonghyun-jo, and we are going to talk about our work, a new metric for an infinity attack today. So, how robust is your model against perturbed input? In this image, with very small adversarial change, the model came to be foolish. Neural networks sometimes produce weird results, even with very small adversarial changes. This non-robust behavior of neural networks can be problematic when the models are used for decision-making in safety-critical systems such as autonomous driving and medical diagnostic systems. In order to determine whether the model is robust or not, we must define a metric to measure it. Sparsity attack. So we are proposing a new metric that captures sparsity of a model against L infinity attack. We commonly evaluate robustness with adversarial accuracy, which tells you for which fraction of the data points there is no adversarial perturbation. Recently, there has been sparse adversarial attacks to modify the smallest amount of pixels in order to change the model's decision. In this case, we need a little different way to measure the sparsity of model. We used CFAR10 dataset to test the model. The CFAR10 dataset consists of 60,000 32 by 32 color images in 10 classes, 6,000 images per class. Images are divided into 50,000 training images and 10,000 test images. We simulated an attack scenario. Basically, we generated noise matrix based on the L infinity norm. The pixels of noise were randomly selected by using a uniform distribution according to the epsilon value for each RGB channel as shown in the formula on the left figure. And then, by combining original image with the noise, we generated a tagged image so as to feed it into a model. For example, in the noise image, you can see about 16 pixels were perturbed. And then we applied our L infinity sparsity algorithm to find the sparsity value k. This figure shows our pipeline to find the value k. As shown in the figure, after random sampling of multiple images per class, images come to be changed to the attacked images, and then we measure accuracy of the model to extract the sparsity k. Here is the pseudocode and visualization of our algorithm. First, a test set is created by collecting a certain number of images from each class. Second, L infinity attack is performed using the specified epsilon value and the current k value for all images. Third, if the model correctly classifies more than half of the images, it will increase the number k. In the opposite case, it decreases k, and then it repeats the sparsity check until k converges. The following is the part about the chem sparsity metric that is currently being added. We discovered the following problems while performing the above sparsity metric. So, to sum up, it was difficult to obtain the minimum number of pixels required for model disturbance. In order to measure sparsity more effectively, it is necessary to limit the area of the noise. It is more accurate to measure the sparsity of the image, specifically for the part which dominantly affects the output of the model. In this context, chem sparsity limits the area of L infinity attack by using activation map. The picture is the result of L infinity attack process when chem sparsity is applied. Let's discuss our experiments. We measured adversarial accuracy and our metric sparsity in the resonant 18 and wide resonant. When measuring adversarial accuracy, two attack methods of PGD were used in our experiments. Specifically looking at the significant result, we can note that wide resonant 70 using code-mix DDPM defense. The accuracy was better than all other cases. However, for sparsity, it had quite bad result. One more thing to note is that SPS defense method was very robust against the sparsity metric. So conclusion, in recent study, adversarial accuracy was not sufficient to capture all robustness properties. So we propose a new metric that captures various robustness properties for adversarial attack, sparsity. Thank you.